Okay, thank you. Well, this is my last lecture, and I guess so yesterday we talked about the consistency condition for symmetry fractionalization patterns. It was a bit formal. I thought it was a very nice structure, a very nice mathematical structure, so I wanted to show you that. But today I want to try to focus more on examples. I hope that's more clear. So, okay, so yesterday we talked about this how to describe a set of consistent symmetry fractionalization patterns in terms of the projective fusion rule of symmetry fluxes with anyon coefficient. So let's assume that we can do that, and that's all done. We take a topological order with a set of anyons, and we take a certain group of symmetry, and then we solve the equation that I wrote on the board yesterday, whatever the equation is, and we get a bunch of solutions. And then the next question is, how do we know if certain solutions can be realized in a two-dimensional model, right? So, of course, we're talking about interacting models in general. So, so if you want to do exhaustive search, then be my guest. But it's in principle, it can be a very hard problem because we're not restricting to any type of interactions or any lattice or any structure, just any local two-dimensional model. So one approach is, of course, if we are smart enough, we can come up with ways to construct models to realize the ones that are indeed possible. So I showed you two examples on lattice yesterday, which are toric code with translation symmetry. But lattice models are hard to come up with. You need to design the Hamiltonian such that they usually you need them to commute. If they don't commute, then it becomes not exactly solvable, and we don't really know what is going on. But there's a very simple, a very powerful field theory structure that can be used to deal with these kind of topological order together with symmetry kind of phases. This is the Chern-Simons theory framework that I want to tell you about today. So I don't want to go back history and start from fractional quantum Hall and show you how Chern-Simons theory comes up and why it describes the kind of physics that we see in two-dimensional electron gas or electron liquid. I just want to write down the formula and tell you, if you look at this Lagrangian, if you look at this field theory description of the topological phases and the symmetry action, how do you read from it the kind of symmetry fractionalization pattern it has? Okay, so I don't want to explain where the formula comes from because I only have one lecture left and I still want to talk about anomalies. But I do want to show you if you want to know if certain symmetry fractionalization pattern can be constructed in this way, how do you try? How do you write down things and do simple calculations and see if that gives you something you want? Okay, so so Michael has a paper on this part, which is very nice. If you are really interested, I suggest you all read that. That's the fractional topological insulator classification paper. All right. So I'm only going to talk about the abelian U1 Chern-Simons theory with multiple component. And when we write down a field theory, we don't normally write down the Hamiltonian, we write down the Lagrangian. And the Lagrangian looks something like this. Okay, so let me explain this notation. Okay, this is the curl L. This is Lagrangian. So first, these labels, lambda, mu, nu, they're space-time labels. So they either are time or two spatial dimensions because we live in two dimensions for now. And correspondingly, we can write 0, 1, 2. So these subscripts take value in this set. And of course, we want to sum over all repeated indices. Just take Einstein's convention. Okay, and this epsilon is 1 if the labels go as 0, 0, 1, 2, 1, 2, 0, 2, 0, 1, and it's -1 if the labels go as 1, 0, 2, 2, 1, 0, 0, 2, 1. So we need all three labels to be different. And also, if they go cyclic, then it's 1. If they go the opposite direction, then it's -1. Okay, and these the A's, they are the U1 gauge fields. And we have sublabels for them. These I's take value in integer. And we can have I being 1 and 2, 1 and 2 and 3, depending on the theory you care about. Okay, so if I just write A, you should consider that as a vector of U1 gauge fields. This K is the most it contains the most information in this Lagrangian. This is an integer matrix. Let's say this label I takes value in 1, 2, and all the way to P. And then this K is a P by P matrix, integer matrix, and we want it to be invertible and also symmetric. So this abelian Chern-Simons theory becomes in many ways a study of these integer matrices, because that encodes all the topological information of this model. Okay, so by writing this down, of course, we're just specifying the theory, the topological part of this theory, and we can read from this K matrix what kind of quasi-particles there are and what their statistics are. For example, in the simplest case, we have just one component of the U1 gauge field. So, and K can just take the value of 1. And then there's only one component of this A, and the Lagrangian becomes something like 1 over 4 pi, and we can use the short notation of A wedge dA. So this is exactly this big thing written here. It's A wedge dA. And this describes the integer quantum Hall. Well, more generally, we can have K be a matrix. And then what happens is that the anyons in the theory will correspond to vectors, a P component vector which we label by L. So there will be integer L1 to LP. So this is integer vector. And if we want to know the statistics of these integer vector labeled anyons, what we do is we can just simply calculate them as theta L equal to pi L transpose K inverse L. Okay, so this is just linear algebra. And we can check what happens for integer quantum Hall. For integer quantum Hall, it's one-dimensional matrix. There's only one U1 gauge field, and L can equal to 0, 1, 2, right? And if it equals to 1, and we plug it into this formula, we find that this is equal to pi, right? And pi is the exchange statistics of a fermion. So this, the L equal to 1 vector just corresponds to the electron in the integer quantum Hall system. And there are no other fractional particles in the integer quantum Hall because it's is non-fractionalized quantum Hall system. Okay. So this is self-statistics. And if you want to calculate the mutual statistic, the braiding statistics of one particle going around another particle, then we involve two anyons, L and L prime. And this is 2 pi L transpose K inverse L prime. So again, very simple algebraic calculation. Okay, and you can see that if L and L prime are the same, then this is just twice that number. That's the full braiding between two identical particles. Okay, and then the ground state degeneracy on a torus, or in equivalent terms, the number of species of quasi-particles degeneracy is given by the determinant of the K matrix. And we take the absolute values so that it doesn't become negative. Okay. All right, this is pretty much all I need. So if k is equal to 1, it's the integer quantum Hall without fractionalization. But in general, we can have k be larger than 1, right? Let's say k is equal to 3. Then what happens is that this k inverse becomes 1 over 3. Then if we calculate statistics of elementary excitation labeled by L equal to 1, this number becomes 1/3 of that in the integer quantum Hall. That's the 1/3 quasi-particle in the fractional quantum Hall system. So this theta 1 becomes pi over 3. So it's very simple. So nu equal 1/3 integer quantum Hall are just given by k equal to 3. And of course, the other topological order which we talk about a lot is toric code. Toric code, we need two components of gauge fields. And the K matrix is 0, 2, 2, 0. And we can see why that is the case. First, we calculate the inverse of K, which is 0, 1/2, 1/2, 0, right? And then we take the elementary integer vectors. So now it's two-dimensional, so there is a L1 equal to 1, 0. And there's another vector, L2 equal to 0, 1. And if we plug it in and calculate the self-statistics, theta 1 equal to 0, theta 2 equal to 0. Because the diagonal term of this K matrix are 0. And if we calculate their mutual statistics, theta 1, 2, it becomes pi, right? So these two just corresponds to the E particle and the M particle, and their composite, we write as 3, which is 1, 1, will correspond to the fermion in the toric code. So it's just that simple. You just take an integer matrix, take its inverse, and then you can find all the statistics. Okay. And of course, I didn't explain why that's the case, and I guess Xiaogong has a paper explaining all the origin of this, and you can go read that if you're interested. Okay, so this is what happens in the bulk of this multilayer Chern-Simons theory, multilayer, and such that we can calculate statistics of the anyons just using the K matrix. But just like in quantum Hall system, we're also interested on what happens on the edge, right? And correspondingly, we can write a very simple Lagrangian for the edge excitations, because in many cases, we can have, in the simplest cases, we can have gapless edge modes around these these fractional quantum Hall samples. So the edge theory is described by another set of fields, which I write as phi. And the phi's are also labeled by these integers going from 1 to p. So corresponding to these A gauge fields, there are these phi fields. And these phi fields, you can think of them as chiral boson modes living on the edge of fractional quantum Hall system. And they take value. So these phi's, they take value in 0 and 2 pi. So it's a periodic field. Okay, and the Lagrangian on the edge looks like something like this: 1/4 pi Kij. Again, this K matrix showing up, and partial x phi I and partial t phi j. Okay. Okay. So these phi fields are just in correspondence with the A fields. And if we want to see how to create anyons on the edge, we can take the exponential of these phi fields. It's just like these phi fields are describing the phase of a boson field. And if you want to know how to, the creation operator of a boson is just to take exponential of these phase factors. Right? So the creation operator, anyon creation, is given by e to the I L transpose times phi. Of course, here the phi is a vector of all the p fields, and L is another p-dimensional vector, and we take the dot product between the two. Yes, exactly. On the edge. Okay. And we want to talk about the edge, even though we're just talking about symmetry fractionalization, because it turns out that anyon creation on the edge is very simple to be just written in this form, while anyon in the bulk it's more complicated. So people usually want to go to the edge in order to even see the symmetry action on the anyons in the bulk. All right, so now we have this formalism, we can start to talk about symmetries. Symmetry transformation. Symmetry transformation of this topological theory can be given in terms of these phi fields. And it goes like this. So this is a vector of boson fields. There's a p component vector, and it goes to W times phi plus delta phi. Okay. So here W is a p by p integer matrix. And this delta phi is a p component vector. Okay. So for every group element, we assign such a transformation to the phi fields. We assign a matrix corresponding to that group element, and we assign a shift of these phase factors corresponding to that group element. And by doing these operations in SQL, we want them to form the group of the symmetry of the system. Okay, let's see some examples. Yes. Sorry, this is a matrix multiplying this vector, and this is just a vector on top of that. No, this is like a linear term. This is like a constant term. Yeah. So we'll see examples. Okay, so one thing I want to mention is that if we plug this transformation into here and see when this transformation is a symmetry. Yes. Sorry? Let me say that. Okay. So first of all, we want to plug this in to here and see under what condition is this Lagrangian invariant, because then we have a symmetry of the system, right? When we plug this in, this part actually doesn't show up because we always take the partial derivative in writing this Lagrangian. So delta phi just disappears. We don't see that. But what happens is that this W goes into redefining these phi's, and they get multiplied with this K matrix, right? So in order for the Lagrangian to be invariant, we want W transpose K W to be equal to K for the edge theory to be invariant. Yes, we want global symmetry. So yes, it's constant in space-time. Okay. You could, yes. Yes. In toric code, if W is 0, 1, 1, 0, it actually switches the two vectors and it permutes the two anyon.
Do you literally mean the two, or do you mean you also redefine your anyons?
Yes. In that case, then you redefine your if the W permutes. Oh yeah, right. Right. You want this
freedom.
Yes.
To redefine K, redefine your anyon.
Yeah.
Charge assignments, such that the project is such that the contraction.
Yes. If you take that degree of freedom into account, then any W matrix keeps the theory invariant, right? So this K matrix is, of course, up to redefinition by conjugation by integer matrix like this. This is just redundancy in the definition of this theory. But once you have fixed a definition of K matrix, once you have fixed which vector corresponds to which anyon, then you do want this to be invariant, for the theory to be invariant. Otherwise, anything is a symmetry. Right. This is actually a good point I want to write down here. That let me see before I start talking about symmetry. Okay. I want to add a point here that for any integer matrix, let's say M, if we redefine K to be M transpose K M, then equivalently, if we map L to M inverse L, then the whole theory is equivalent to the original one. Because if you calculate statistics, the M and M inverse just cancels out, and you get the same number. And you get the same species of anyons, you get the same braiding statistics, it's the same topological order, even though the matrix and vector, they look slightly different. Okay, so this is a large group of redundancy in writing this K matrix. I should say this is equivalent theory. This yes, determinant where it. Sorry, who is speaking? Oh yeah, and the one who knows best. Yes, you want the determinant to be 1. Can it be minus 1? Yes. Just the absolute value to be 1. This is required so that we have so the determinant of K is still the same. Yeah, the ground state degeneracy. Right. But once we have fixed a description K for the theory, and if we want to talk about symmetry on top of that, then we don't want to we want to forget about this redundancy. Otherwise, everything's a symmetry of the theory. So so this is required for W to describe a symmetry of the theory if this is describing a unitary symmetry. On the other hand, if W is describing anti-unitary symmetry, which is involves time reversal, then there's a T here. So this T will go to minus T on the time reversal. And there's an extra minus sign coming up in front of the Lagrangian. Okay, that's just by doing nothing, but just by saying we want the symmetry to do time reversal, and then automatically there's a minus sign in front. So in order for the theory to be invariant, we want W transpose K W to be equal to minus K. Okay, just to cancel that minus sign coming up from T goes to minus T. Oh yes, that's a great point. So if you do spatial inversion, there can be a minus sign coming from here, and you absorb that. Okay. Or unitary internal unitary symmetries. So this is for time reversal. Okay. So now we can play with it. Let's say we want to talk about toric code. So this is just examples. Let's say we want to talk about toric code with K matrix 0, 2, 2, 0. Okay, and we already know that the E particle corresponds to the vector 1, 0. The M particle corresponds to particle 0, 1. And the fermion corresponds to particle vector 1, 1. Okay. And now, let's say we want to consider a Z2 unitary symmetry. First of all, let's consider the case where the Z2 symmetry doesn't permute the anyons. Okay, so if it doesn't permute the anyons, we want 1, 0 to still go to 1, 0, and 0, 1 to still go to 0, 1, right? So the unitary symmetry, in the simplest case, W can be equal to just identity. We don't want it to permute the anyons. But we can have a non-zero delta phi. Delta phi actually is pretty, we didn't put any constraint on it in order for the theory to be invariant because it just doesn't show up once we take the partial derivative, right? But it does have the constraint, right? If we wanted to describe a Z2 symmetry, we want to do it twice and get back to the original theory, right? So here, delta phi, for example, can be pi 0. That's saying that this phi 1 goes to phi 1 plus pi, and phi 2 doesn't change. Doesn't change. Okay. And the consequence of this is that the quasi-particles, the creation operator for the quasi-particles, they transform under the symmetry. So remember that if we want to create anyon, we just take exponential of these phi fields. And you can see that the anyon creation operator of the E particle, which is e to the I phi 1, under this Z2 symmetry, it gets a minus sign. And the creation operator of the M particle, that does not change. Okay, so it's somewhat like saying that this E particle carries a Z2 symmetry charge, while the M particle doesn't. But of course, this is totally up to definition, because we know that these kind of integer charges is not intrinsic to these fractional excitations. Integer charges, we can just add them on top of whatever fractional excitation we have. Like in fractional quantum Hall system, we can attach an extra electron to this quasi-particle and change the charge by 1. So that's like a non-intrinsic part of the symmetry fractionalization pattern. Only the fractional part is intrinsic to each species of anyons. Yes. Sorry. So the M vector is 0, 1. And it changes to W times 0, 1, which is still plus this phase factor. I should write like this. This is phi 1. This is 0, phi 2. Sorry. Let me rewrite it. So the symmetry transformation. Well, the symmetry transformation is that this phi has two components. If I write it in the vector form like that, it's phi 1, phi 2. And W is identity, so nothing happens. So it's phi 1, phi 2 plus pi 0.
So when you write the vector part, that's not an integer. I guess why?
Oh, so okay. So the E and M, when you write the creation operator, you want to take the dot product between the L vector and the phi field. So the vector corresponding to M is 0, 1, dot product with phi 1, phi 2. This gives you just phi 2. Yeah, okay. Yeah, I skipped that step where I take the dot product between the vectors. Okay, so this is some Z2 transformation, but it's a not very interesting one because there's no fractionalization going on. It's pure integer charges. But what we can do is instead assign Z2 symmetry to transform as phi 1, phi 2, going to, again, the W matrix, we want it to be 1. But this one goes to pi over 2, 0. Okay. And once we do that, then there's fractionalization because the E particle under Z2 symmetry, it gets a phase factor of I. And that's a fractional Z2 transformation. Because if we do it twice, we get a minus 1. But on the other hand, the M particle doesn't change at all. So this is fractionalization just on the E particle part. Okay. So this is given by this pi over 2 phase factor. All right, and then we can come up with more examples. If we want both E and M particles to transform in a fractional way, we just assign the Z2 symmetry to be phi 1, phi 2, going to phi 1, phi 2, plus pi over 2, pi over 2. Okay, so just play with that, right? When the symmetry acts like this, then both E and M get a I phase factor on the unitary Z2. And the good thing is that once you can write down things like this, you know that this is doable in 2 dimensions. It's a well-defined field theory, and we can calculate statistics, we can calculate symmetry charge, and it's doable in 2 dimensions, even though we might not be able to come up with an exactly solvable lattice model. Lattice model is, in general, much harder. Yes?
How can I see this as Z2 symmetry?
Oh, yeah,
Instead
right.
of Z4?
Yes, good point. So this phi fields, it looks like it takes 4 operations to get back, right? But remember that what happens is, what matters is only these. You only want to look at how the quasi-particles transform under the symmetry. But the quasi-particles, they're not individually local excitations of the system, global excitations of the system. When you create them, you always create pairs. So as long as a pair of that transform under this Z2 symmetry, acting Z2 symmetry twice, get back to the original excitation in the wave function, then we're fine. So these fields are actually a little bit fictitious.
For example, can I do pi over 3 here?
Yeah, that's a good question. Then they won't be fine, because if you look at how the anyons transform, there will be some strange phase factor of pi over 3. And even if you put 2 anyons together, that phase factor doesn't get back to 1. Yeah.
One.
Yeah, sure.
What about I just do one Z2? So if I just do one so-called Z2, I get also a phase factor. So why isn't it just an identity operation?
Right, so you have a system. You create 2 E particles, right? And you do Z2 transformation, you get an I here and an I here. So globally, you get a -1, but that's okay. Globally, Z2 symmetry can give you a -1, because it's the quantum number can be 1 or -1. Yeah, so you need to remember that the anyons, they come in pairs, and put their quantum number together and see if it's an integer. Yes? Oh, you just realize that they have statistics either among themselves or with other quasi-particles. So whenever the statistics are non-trivial, the anyons can't be created just out of vacuum. They have to come in particle and antiparticle pairs. Right, you can't just create something in vacuum such that it breaks with other things. That just doesn't happen. Yeah. Right, very important questions. Okay.
So I really missed this symmetry. Like, it seems arbitrary.
You are expert on this. I'm afraid of you have hidden meaning of this question. What do you mean?
Well, I mean, so what?
So we assign transformation rules like that, and we want it to be a symmetry, so that we want this to be satisfied. But then the delta phi part, we just look at how the quasi-particles transform, whether they get a phase factor like that. And if the particle and antiparticle pair, the phase factors combine into a well-defined quantum number, then that's fine. Are you thinking about the U1 case?
Well, I'm just wondering, what are the constraints?
The W is that constraint. Right, this is just yeah, so if this is pi over 3, Then doing Z2 symmetry twice, we would get e to the I 2 pi over 3 for one e particle, right? But then if you have two e particle in the system, it will be like e to the I 4 pi over 3, which is not a Z2 quantum number in any way. So we either have pi or pi over 2, but that's it. We can't have arbitrary numbers. Yes, yes. So you need to take into account the order, in some sense, of the anyon that transforms under this symmetry. You want to make sure that certain copies of this symmetry transformation give you an integer representation.
Okay, so you declare transformation under which you want to be invariant, and then you constrain itself.
Yes.
How phi is
Yes.
Like if it was C3.
Oh, yes. Yes. Exactly. Yeah. Yeah. These three, doing 3 times, we get pi on each e particle, and 2 of them gives you. Yeah. Yeah. Thanks. Right.
For the fractional quantum Hall, the particle and the atom are also
Yes. Yes. So the question was, in fractional quantum Hall nu equal 1/3, we either create a charge 1/3 and a charge minus 1/3, or we create 3 of charge 1/3 out of 1 electron, right? Is that a question? Okay, yeah. Yes, so if you have 3 charge 1/3, you can think of these two as a composite that gives you the charge 2/3. As long as they add up to some integer, then that's fine. Yeah. Okay, great. So this is the Z2 example. So we see that we can make the E and M particle to transforming anyway under the Z2 symmetry. It's pretty flexible. We can have E have fractional charge. We can have M have fractional charge if we reverse this, or we can have them both to have fractional Z2 charge. Okay. Now let's go to time reversal. Okay. So we want still again Z2 toric code with K matrix 0, 2, 2, 0, and time reversal. Now, if we want time reversal, this W matrix cannot be trivial, right? If it's trivial, we cannot get a minus sign in front. So we want some W transpose K W equal to minus K. Okay. And then on top of that, we can still have this delta phi phase factor. Okay. So let's see what can happen. Where did I write it? Okay. So the first one is phi 1, phi 2 goes to phi 1 minus phi 2 plus 0 pi over 2. Okay, so the W matrix is this poly Z matrix, and it indeed anti-commute with the K matrix of 2 times sigma x, right? The anti-commute. But there's also this phase factor. And then we can look at how the quasi-particles transform. So it's e to the I phi 1. On the time reversal, nothing happens. Do it again, still nothing happens, right? So the E particle transform in a pretty trivial way. The M particle, on the other hand, e to the I phi 2 goes to I times e to the minus I phi 2. And we do it again, we get minus e to the I phi 2. Yes?
Is there a reason why e to the I doesn't go to e to the minus
Right, good question. Should I? I think it should, yeah. Although it doesn't, the I gets reversed. Yes, thanks. That's a good point. Although it doesn't affect because you reverse it twice, then it gets back. Thanks. Yeah, really. Yeah. Okay, I missed this minus sign. So this one actually has plus. No, because phi 2 goes to minus phi 2. Oh, you're right. Yeah, this one doesn't change. Right, good, okay. Yeah, thanks for catching all my mistakes. So, right, this one goes to plus. Yeah, this is correct. Okay, and the important point is that there's a minus sign here. Okay, good, great. So this is saying that time reversal twice on the E particle doesn't do anything. Time reversal twice on the M particle gives you minus sign. So it's T squared equal to minus 1 on the M particle. And that's a Cramer doublet. Okay. And the Cramer doublet is a twofold degeneracy on the time reversal, so it has very explicit measurable consequence in the model. That is, if you create a pair of M particles and pull them apart, then on the time reversal symmetry, there's a fourfold degeneracy. Okay, so we can have the M particle transform in this non-trivial way, and similarly, we can have the E particle transform in this non-trivial way. We just flip everything, right? We can just redefine. We can switch the definition of phi 1 and phi 2, and we can have the E particle transform like this. But can we have both of them transform like this? Can we have both of them transform as T squared equal to minus 1? We can try to play with that. I tried a few ways. Okay. Let me see. So if we do this, okay. So I tried like phi 1 goes to minus phi 1 plus pi over 2, and phi 2 goes to minus phi 2 plus pi over 2, right? This seems to work out if you calculate how the quasi-particles transform under time reversal. There indeed will be minus sign here, because the transformation rule follows the form of the phi 2 in this case. But however, in this case, the W matrix just becomes minus 1, minus 1. It no longer anti-commute with the K matrix, so it's not really a time reversal symmetry. It's actually a unitary Z2 symmetry doing this. So it actually gives you the same thing as what happens here. That the two quasi-particles carry unitary fractional charge. It's not really a time reversal fractional representation. So this one doesn't work. Okay. Then I can try something different. Oh, I didn't try something different. Actually, I don't know what to try. So this one is actually anomalous. This is what's called the ETMT, according to Sentiel's terminology, that E and M particle both transform as T squared equal to minus 1 on the time reversal. So this one, yesterday we looked at the equation, and I explicitly said that it's a consistent symmetry fractionalization pattern. Of course, if E and M both transform as T squared equal to minus 1, then the F particle will transform as T squared equal to plus 1. And in that sense, the whole symmetry fractionalization pattern is consistent, but however, it it's just impossible to write down a two-dimensional field theory to describe it because it's anomalous. But of course, at this point, we don't know that. We just know that we tried using this formalism to write down a field theory describing this pattern, but we failed. Yes. I see. I never tried with SO3. What's wrong with SO3? It's pretty yeah, a billion. Yeah. So if you want the E particle to carry let's say a spin 1/2, then definitely you need the internal structure to the E field instead of just yeah, like that. Okay. But there's a different thing. Yes.
It seems like the delta I is really the only thing that so why we choose 5 to 5 1 plus 5 2 and 5 2 goes to minus 5.
Oh, okay. We can try. So. So you're saying something like this, right? Okay. So e to the I phi 1 goes to, let's see, I e to the minus I phi 1, which goes to minus I e to the I phi 1 plus pi over 2, right? And there's a minus I here, and an I coming from here. This is still e to the I. Sorry? Yeah, there's a minus sign here. That's crucial. Okay, so let me do this phi 2 case more carefully. It's e to the I phi 2 goes to I e to the minus I minus phi 2. And then, okay, I'll finish this. So it's minus I e to the I minus phi 2 plus pi over 2. Yeah, if you do the algebra, then there's a minus sign. Okay. Yeah, somehow the minus sign is very important, yes.
Shouldn't there be an extra minus for the last line?
Here?
Yeah, the second arrow, because I goes to minus
I.
No, the I next to it. Not that.
Yeah, so this is my derivation here. Okay, so I'm just writing this line in a more extended way. Okay, so this is e to the I phi 2 goes to, and this I comes from this pi over 2. Okay, and then e, and then I goes to minus I, and phi goes to minus phi 2. And let me just first combine everything. So there's just a I in front. And then we do it again. So I goes to minus I, e to the, right, there's the minus sign. Right, so this is minus I going to I. Minus phi 2 goes to minus phi 2 plus pi over 2. So you just write everything out very carefully. Every I goes to minus I, and the phi 2 goes to minus phi 2 plus pi over 2. And so this is minus I. This is e to the I phi 2 minus pi over 2. So there's a minus I coming from here. Combined with the minus I here, gives you a minus sign total. Yeah. Yeah. Okay. So the next thing is whether we can have time reversal exchange E and M. Okay. So we can try to do things like, if we want to exchange particles, we can do W equal to 0, 1, 1, 0, right? That will switch E and M. Okay. But this one is bad because this one commute with the K matrix. So it's not a time reversal symmetry, right? So W transpose KW is equal to K. So this is not time reversal symmetry. And we can come up with another matrix like W equal to 0, 1, minus 1, 0, which does flip 0, 1 and 1, 0, although with an extra minus sign. It seems to exchange it seems to exchange E and M and also anti-commute with K matrix, right? But however, the problem with this one is that if we actually see what happens to the quasi-particle, this one goes to e to the minus I phi 2 and goes to e to the minus I phi 1, and this is e to the I phi 2 goes to e to the I phi 1, which goes to e to the minus I phi 2. Okay. So we started from a vector of 1, 0, and doing time reversal twice, we get a vector of minus 1, 0. Okay. So if you use minus 1, 0 to calculate all the statistics, or either self-statistics or mutual statistics with anything, you get the same result. But however, so this is just saying we get back to the original quasi-particle type. That's good. But they're different things. They differ by some local excitation, which is given by this e to the minus 2I phi 1. This thing doesn't contribute statistics, but it is some local excitation. So by doing time reversal twice, even though the quasi-particle type goes back to the same type, we create extra local stuff at the point of the anyon. So this is not really a symmetry of the theory. So this also doesn't work. And in Chern-Simons theory, even though we can write down a way for Z2 theory to exchange E and M, I can't write down a way for time reversal symmetry to exchange E and M. But on the other hand, we already saw an example where time reversal exchange E and M, right? We talked about this last week. We started from topological superconductors. We gauged the Z2 part of the symmetry, and we see that time reversal does exchange E and M. Okay. So this is just saying that sometimes we can't write down a theory because it's anomalous, like in the ETMT case. Sometimes we can't write down a theory because of the limitation of the formalism, and we just don't know. And this becomes more serious if you do a lattice model, because lattice model is even something very natural here. We don't know how to write down explicitly exactly solvable models for that. So it becomes a question of how do we go beyond formalism to tell whether some symmetry fractionalization pattern is anomalous or not. And I can see I only have half an hour, and I'll try to at least give you some examples of how to detect anomalies.
So did you say this is anomalous?
This is not anomalous because we know that gauging topological superconductor gives you this one. So it is.
ETMT is anomalous.
Yes, yes. And that is totally not obvious why one is anomalous, one is not. Yes, it's just you try to write down two-dimensional theory, either use lattice model or gauge theory, and you can't do some of the things. Sometimes it's because the limitation of the formalism. Sometimes, like for lattice model, it's usually because we just don't know how to write a lattice model. Can be quite complicated. Yeah. Oh, all right. Okay. So let me talk about anomalies.
One comment after here, I don't know if it'd be helpful, but this example that is not anomalous but we couldn't realize is kind of special in some sense because it's edge theory. I guess I missed your discussion, but you got it from a topological superconductor, so you kind of know the edge involves these Majorana's. It's not a chiral boson edge theory.
Yeah.
It involves Majorana's. So
Yeah. 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 Exactly. Yeah, that's a great point. Yeah. So if there's anything non-abelian like that, then it's you can't describe it with abelian Chern-Simons theory at least. But of course, if you don't know about the edge theory and or don't know that it comes from topological superconductor, just looking at this symmetry fractionalization pattern, it can be hard to see. But yeah, thanks. That's a great point. Right. I lost track of my section number, so I'm just using dots. Anomaly detection. Okay. Right. So let's consider a prototypical example where I want to start discussion of anomaly, which is what is called the ECMC. Okay. So here C means charge. We have a U1 symmetry, and also we have the Z2 toric code. We have Z2 toric code with identity E and M and F, and we have a U1 symmetry where this one carries half charge and this one carries half charge. And of course, if these two carry half charge, this one doesn't carry half charge. I'll just write a 0. It's just to mean integer charge. Okay. And if we try to use the K-matrix formalism to write down how the fields transform under U1 symmetry, and if we write a transformation under the U1 group element corresponding to phase factor alpha, it goes like phi 1 plus alpha over 2. And phi 2 also goes to alpha over 2, right? So after 2 pi rotation, there's actually a pi phase factor, and the quasi-particle accumulates a minus sign because it has half charge. So if alpha is pi, then it exactly goes back to the Z2 situation we talk about here. So this one, we can write it down with Chern-Simons theory. So when that is the case, we know it's definitely not anomalous. Okay, that's good. And then the question is, what if I add time reversal symmetry? What happens there? Okay. So it's not obvious what time reversal does here, because this particle has half charge, this particle has half charge. If time reversal doesn't reverse the charge, then if I apply time reversal, this thing still has half charge, this thing still has half charge, right? There seems to be nothing wrong with adding time reversal symmetry to this fractionalization pattern. Okay, but then I can go to the edge and, then what I can do is to write the theory coupled to the external electromagnetic field. So originally, I just have this term. Too sloppy. Now, because the fields carry charge, I can write them as coupled to this external gauge fields. external gauge field, I write it as big A. It's E over 2 pi. This is the electron charge, units of charge, and with a vector of 1, 1. Oh, I guess not everyone can see now. That's bad. Can everyone see? Let me copy it somewhere. So I'll not copy the topological term. The first term, I'll just ignore it. And not just the same as toric code. The second term is so tau I is the vector of 1, 1. Tau is the vector of 1, 1. Okay, and tau I are the components of this vector. Okay. And when I write things down in this way, I don't want to derive it, but the result is that you can calculate how much charge each quasi-particle carry. And that's given by tau transpose K inverse L. So this L labels which quasi-particle you care about. This is the K matrix describing the topological order. This is what we call the charge vector. So do this calculation, you find out how much charge E carries, how much charge M carries. And if in this case with 1, 1, then both of them carry half charge. It's 1/2 this number for both E and M. And then what we can do is to integrate out all the little a fields and only leave behind the big A field. So that really becomes a response theory to external electric magnetic field. And there comes a Chern-Simons term. For this big A field, which is equivalent to say there can be a non-zero Hall conductance for the external gauge field. So I don't want to do that calculation, but just to write down the equation of sigma xy equal to tau transpose K inverse tau. Okay. So these are really amazingly simple formulas. You just put the charge vector in here and combine with the K matrix, you get the Hall conductance. And if we do the calculation here, you will see that this is 1. Okay. So there's 1 unit of Hall conductance. That means this is pretty much like it's very much like integer quantum Hall, that we have H modes carrying charge going around the sample, even though we also have fractional quasi-particles in the bulk. So there's E particle with 1/2 charge, M particle with 1/2 charge, and the sigma xy equal to 1 in units of E squared over H. Okay. Right. So now you can see what's wrong with time reversal symmetry. If the system is time reversal invariant, then supposedly if we put the system on a disk, there should not be a Hall conductance. Right? Hall conductance explicitly breaks time reversal symmetry. And even though if we look in the bulk at how much charge the quasi-particle carries, there seems to be nothing wrong with time reversal symmetry. If we look at the edge, there is such a Hall conductance. Okay. And this is Right, this is why this ECMC symmetry fractionalization pattern plus time reversal becomes anomalous. This is very, very similar to the case of topological insulator surface state, if you think about it. Usually when we talk about topological insulator surface state, we say there's a single Dirac cone, right? And if we look at a single Dirac cone, it seems pretty nice on the time reversal symmetry, right? The spin goes around the cone, and if you map k to minus k, then the spin also reverses. So it looks pretty much fine until we realize there's a theta term in the effective theory description, which corresponds to the fact that the edge theory, if you really put it in 2D, there's a 1/2 Hall conductance. Okay, so compared to here, this is a 1 Hall conductance. But in the case of fermionic topological insulator, the single Dirac cone, if we put it in 2D and gap it out, there's a 1/2 Hall conductance. Yes.
Does the sigma xy also have a sign ambiguity?
Yes. Yeah. So, okay. So that is a very good question. So, so there's something called a bosonic integer quantum Hall. Let me just make a brief comment that which has a Hall conductance equal to 2. So if you add a -2 on top of that, you get a And so it's ambiguous up to 2. Yeah, although the fractional the topological insulator surface is ambiguous up to 1. But this ambiguity is not 1. That's why this is yeah.
For bosonic system, sigma
Yes.
xy equals 1 is
Yes, yes, exactly. Good point. Although I don't have time to explain that. Right, and this is very, very similar to what happens to fermionic topological insulator, and this is actually what happens on the surface of bosonic topological insulator. Right? In this theory, there's no fermion, there's no electron. It's just a bosonic model with the quasi-particles carry potentially half charge of the theory. And this symmetry fractionalization pattern, together with charge conservation, together with time reversal symmetry, cannot be realized in 2 dimensions. But however, it can be realized on the surface of a 3-dimensional bosonic topological insulator. And by bosonic topological insulator, of course, I'm not referring to any band structure. I'm not referring to things like Liang talked about yesterday. There will be a strongly interacting model because bosons, if you don't add interaction, they just condense, right? They don't feel a band structure. So there's strong interaction going on, and by topological insulator, I just mean that this is a model with time reversal symmetry plus charge conservation symmetry of U1. Actually, I should write the semi-Dirac product. Okay. The similarity with the fermionic version of topological insulator is still that the edge state will be non-trivial. But usually when we talk about fermionic topological insulator, we say that the edge state is single Dirac cone, right? Single Dirac cone means it's gapless. Or we can break time reversal symmetry or charge conservation symmetry. In that case, we can gap out the Dirac cone. We can gap out Dirac cone by putting magnetic field or proximity to a superconductor. In both cases, the surface state gaps out, but only by breaking symmetry. But however, here I'm talking about a third possibility for the surface state of 3-dimensional symmetry-protected topological faces. That is, it can be gapped. This is topological order. It's gapped, and also it's fractionalized. It doesn't break the and also it doesn't break the symmetry. There is still time reversal symmetry. There is still charge conservation symmetry. It's just that the surface has to be fractionalized with anyons, and the anyons transform under symmetry in a non-trivial way, which is related to the bulk topological order. Okay, so this correspondence between symmetry fractionalization patterns and the bulk order is exactly the same as the correspondence between single Dirac cone and fermionic band structure. They are intimately related, and they don't. This kind of surface states cannot live on their own. They must live on the surface of something. Okay. Yes, exactly. If you break time reversal, you can have Hall conductance. Then this is okay in 2D. Sorry? What do you mean original spray degree?
I write a macroscopic model.
Oh, okay. Oh, you can imagine that the system is composed of bosons, charged bosons, and yeah, they can form. You want the spin lattice model?
Yeah. The toric spin formula.
Oh, the toric code, yeah. Okay, so this is in the same. The topological order is in the same universality class as toric code, but if you literally want to write down toric code and do modification to that and give rise to this kind of symmetry fractionalization pattern, I believe you can. It's just a little bit complicated. You need to add charges in there and then combine them in a certain way. Yeah, I think Michael has a paper about exactly solvable fractional insulators, and they're very useful methods for constructing this kind of thing. Yeah, that might help. Okay. Right. So this is just the logic behind the whole thing. That symmetry fractionalization patterns, if they're anomalous, then they cannot be realized in purely 2D model. And this one we can see because we can put the system on a disk and see that the edge state explicitly violates the symmetry that we wanted to have. But on the other hand, it can be realized on the surface. And once it's on the surface, this contradiction goes away, right? Because the surface of a 3-dimensional bulk does not have an edge of its own. This is a very, very fundamental geometrical observation that a topological observation that boundary of something doesn't have a boundary of its own. So the surface of a bosonic topological insulator as a 2-dimensional manifold doesn't have a 1-dimensional edge of its own, unless you, of course, break the symmetry. But if you try to knock out a piece of this bulk, then the surface just goes in, right? It just smoothly continue and still a continuous surface. So we don't actually see this Hall conductance anymore. Once it becomes the surface state, all we see is the fractional charge that appears in the bulk. And the fractional charge has no contradiction to time reversal symmetry. And that's why once it's realized on the surface, then there's nothing wrong. Everyone's happy. All right. So I do want to talk about one more example of anomaly detection. That involves unitary symmetry. Okay. So this is what Mike and I did in this paper called Flux fusion. I want to talk about it because I already talked about how fluxes fuse into anyons yesterday, and I think this is a very simple illustration of the idea behind that. So for time reversal symmetry, we can, in many cases, do this. Although not all time reversal anomalies can be detected in this way, but many examples we can. If we want to see the anomaly on the time reversal symmetry, we just put the system on a disk and see if it has a chiral edge mode. This happens for the surface state of bosonic topological insulator, fermionic topological insulator, and also fermionic topological superconductor. Okay. And because in the case of fermionic topological superconductor, this is a Hall conductor. This is thermal Hall conductance instead of E&M Hall conductance. But for unitary symmetry, it's more tricky because if we put it on a disk, chirality doesn't tell you anything. Chiralities can be totally consistent with unitary symmetry, so we actually need to do something more. And this involves spreading flux through the system and see how they behave. Okay. So this example is, again, with toric code. And some U1 symmetry and time reversal symmetry. And the tricky thing here is that it's different from the symmetry we talk about here. In here, in this case, U1 is in a product with time reversal symmetry, which means that if I take a group element of the U1, it commutes with time reversal symmetry. And because I goes to minus I here, then we need a charge to go to minus charge. So time reversal symmetry flips charge. So you should think of the charge as some spin in the z direction instead of real electron charge coupled to external electric magnetic field. Okay. Although we can just think of it as some fictitious charge here. Okay. So the symmetry fractionalization pattern, as the name suggests, is that the E particle transforms non-trivially under charge such that it carries half charge. And M particle transforms non-trivially under time reversal. And the way we know that it can transform non-trivially is as t squared equal to minus 1, right? So as a chroma doublet. Okay. So this one, because only E particle carries half charge, so the charge vector is 1, 0 in order to create only fractional charge for E, but not fractional charge for M. And once we use that to calculate the Hall conductance, it becomes 0. So if we just put the system on a disk and look at the edge, we don't actually see the anomaly. The anomaly is not explicitly revealed by just putting the system on a disk and looking at the edge. But instead, we need to involve symmetry fluxes of this U1. Okay. So back to the picture of yesterday. Now we can imagine we spread a flux through the system and then bring the E particle around it, or the M particle around it. Okay. And if the flux is 2 pi, then if the E particle goes around it because of the half charge, this gives you a phase factor of minus 1. But if the particle is M, this gives you a phase factor of 1. Right? And there's something else which braids around E with a phase factor of minus 1 and braids around M with a phase factor of 1. And that is exactly the M particle itself. Right? So this is what I spent 1.5 hours yesterday to talk about. That is this projective fusion rule of symmetry fluxes. And in this case, I should write, for example, 5 pi is equal to M phi 0. And of course, phi 0 is nothing. It's doing nothing. It's really vacuum here. So it's just saying that 2 pi flux should combine into an M particle. Okay. So this is just the U1 part. And the U1 part alone, of course, doesn't cause anomaly. If we only have U1, there's nothing wrong. But then we want to remember that there's time reversal symmetry in the model, such that the M particle transform as t squared equal to minus 1, right? Okay. And then we can ask, how do these fluxes transform under time reversal? So usually when we think about flux and talk about their transformation under time reversal, one usually say that flux goes to anti-flux. But that's the case when it's real electromagnetic flux, where the charge doesn't get reversed, but the flux gets reversed, right? So magnetic field, a real-world magnetic field does that. When you apply time reversal symmetry, it goes to the opposite. But here we are talking about a slightly different U1 gauge symmetry, a U1 symmetry, such that it is in a direct product with time reversal. The charge gets reversed, but the flux doesn't because it's direct product. So any group element in here, you add time reversal on that, it's still the same group element. Okay. So this thing, it is actually an invariant object on the time reversal symmetry, and we can actually talk about quantum numbers of this object on the time reversal symmetry action. And there are two choices. We either have t squared equal to 1 or t squared equal to -1. But then there's a problem. On this side, we either have both of them being t squared equal to 1 or both of them being t squared equal to -1. But when they combine together, they should give you t squared equal to 1, not -1, right? So there's no way we can connect these two sides. And there's anomaly. So by thinking of symmetry fluxes and by using the projective fusion rule of symmetry fluxes, and then combined with how the quasi-particles transform under symmetry, we see there's a contradiction in the projective fusion rule and also the fractionalization pattern of the anyon. So this is one particularly nice example to illustrate the idea of Markov flux fusion. Okay, so I have a few more minutes, so just let me say what I didn't cover in this lecture. Of course, this is these are the two very simplest way to see anomaly. With time reversal symmetry, you see chirality. With some simple symmetry fractionalization pattern, we can just look at the fractional the projective symmetry fusion rule and think about how symmetry flux transform under other symmetries. But there are other ways. For example, there's I think a paper by Cho and Xie, and also paper by Ryan and Kapustin, and they talk about if you have two parts of the symmetry, G1 and G2, and if you gauge part of it, and if you can explicitly see that by gauging this part, breaks that part of the symmetry, then there's an anomaly going on. Because if this is indeed a model with this bigger symmetry, then gauging part of it you should end up with a global model still with the global symmetry of the second part. Okay. Sorry. So this is so if you have G1 cross G2, then gauging G1 breaks G2, then you can see that there's something wrong. Because if this can be realized in two-dimensional model, we should be able to gauge G1 without break G2, and then further gauge G2, and in the end gauge everything. But if we can only do part way, and we gauge G1, it already breaks G2, we cannot complete the full gauging process. Then there's something wrong with it. And also, there's actually a big mathematical framework behind all these kind of things. It's called homology, and the object is called a G-cross tensor category. And there's a big mathematical paper by Adinov and some other people on this. I can't understand that paper. And luckily, there's some people who understand it. Lucas taught me all of this, but then several people at Station Q, Pasa Bonderson, Mason, and Zheng Han, they wrote a big paper, and also Meng Cheng, they wrote a big paper on gauging and symmetry defect. It covers a lot of things that I mentioned in this lecture in a very mathematical formal way. They have a big framework to explain how to think about symmetry fluxes and the fusion of symmetry fluxes and the braiding of them. And so in the end, you get a mathematical framework involving symmetry flux and the original anyons in a way very similar but also more complicated than the theory for anyon alone. Okay. For anyon alone, we can talk about their fusion, we can talk about their braiding, and for symmetry fluxes, we can pretty much do very similar things. We can talk about their fusion and their braiding. Of course, some rules are different and gets more complicated, but it's again a consistent mathematical framework to talk about these kind of things. And starting from there, you can extract anomaly. And so we wrote a paper based on that, and it applies to the Z2 cross Z2 symmetry, where you can have a very simple formula. Well, it's not a very short formula. It's a simple formula in the sense that you can directly plug it into the computer and do the computation. So you just take some data from the topological theory and take some data of the symmetry fractionalization pattern, and you plug it in. And then the computer can tell you whether this is anomalous or not. Of course, that theory is based on gauging. It's based on symmetry fluxes. So in principle, it applies only to unitary symmetry. But it turns out, if we plug the data in for this ETMT model, somehow miraculously it still works. So it just suggests that maybe we can think of time reversal flux in a similar way. But I don't want to go too far in that direction. Okay, and there's right. All these anomalies that I talk about doesn't involve exchange of quasi-particle type. There can be anomalies when you permute, when you exchange quasi-particle types, and that's actually a much, I should say, a lower order of anomaly than all the ones I talk about here. So if quasi-particles are exchanged, we should check for a lower order of anomaly. That's something related to this H-3 anomaly. And all the ones I talk about here is related to something called the H-4 anomaly. I don't want to explain here, just in case someone has heard about it, I want to comment on it. So this is all in this big mathematical paper by Adinov and al. And there is a systematic way to calculate whether you have H-3 anomaly or not. But there's a nice physics understanding emerging now regarding what these things mean. Okay. The H-4, it's something. If you have heard about it, it's the fourth group cohomology of a symmetry group. This can describe the anomaly in a symmetry fractionalization pattern. But on the other hand, it also describes symmetry protected topological order in 3D. So it's a coincidence, but also not, that according to this picture, the H-4 data both describes the topological order in the bulk, the symmetry protected topological order in the bulk, and also the anomaly on the surface. That's just saying there's a bulk edge correspondence in this way here, although it's in a highly mathematically abstract way. The H-3 is a more interesting anomaly, and recently there has been work by Lucas and Ashwin, and also Ryan and Anton, constructing examples of this kind of anomaly on the surface of something. So for Lucas and Ashwin, they constructed on the surface of a three-dimensional symmetry-enriched topological phases. So it just piles up, right? We are just talking about two-dimensional symmetry-enriched topological phases, but they're talking about three-dimensional symmetry-enriched topological phases, and that kind of thing can also have a surface. And they can construct models where the surface has these kind of anomalies. And I think there's a paper by Ryan, not Ryan, Anton. Ryan and someone else. They suggest that this H-3 anomaly is associated with some two-form symmetry. Although I have to say exactly understand, but Ryan is supposed to be somewhere, so maybe you can ask him about it. But this is the story. So, right. So I think I pretty much explained the line of thought, examples, and some important tools like the gauging and the Chern-Simons field theory and the fusion rule of symmetry fluxes. I think those are the important ideas that you base on to study things topological order with symmetry. So of course, there are a lot of things that I cannot cover, but I think this could be a good starting point if you want to start reading things in this direction. So I will, I have a lecture note. Of course, I'll have to reorganize it according to what really happened in the class, and I'll try to compose that and put it up. Okay. All right. Thank you. Questions?
And all anomalous symmetry fractionalization patterns be realized at some time.
Right, good question. So for the case where symmetry doesn't permute the anyons, I think that's pretty much the case. So a useful construction that we use to do this kind of thing is the Walker-1 construction. And the Walker-1 construction literally, it's a complicated lattice model, but it literally takes the surface topological order or the surface symmetry fractionalization pattern and write a 3D model out of it, making sure that the input data emerge on the surface again. So that's a very nice way to just start from whatever symmetry fractionalization pattern you have and construct that model such that it becomes the surface. And of course, for the A333 part, I'm not exactly sure. Of course, in that construction, then it becomes a problem of determining what really happens in the bulk. Because we know what happens on the surface, but the bulk is written in a very Walker-1 way, not in any way that's connected to the way we know about symmetry protected topological orders, like band structures of topological insulator. Yes, I actually want to comment more about that. The study of surface state of fermionic topological insulator. So there it happens that 4 papers got posted on one day, and there are 2 Santa Barbara papers and one at MIT and one me and Lucas and Ashwin at Berkeley at that time. There are very different approaches. We use this Walker-1 construction, and the MIT group and the Santa Barbara group, they use field theory derivations to end up to find the surface state. Of course, that is so what you want is to find some symmetry fractionalization pattern such that it's consistent with whatever we know about fermionic topological insulator. And it turns out we know a lot about fermionic topological insulator, like the surface has half-Hall conductance, and if there's superconductivity, the vortex core has a Majorana mode, right? And also it's just somehow if you break time reversal, then it's a trivial state. If you break charge conservation, it's a trivial state. So if you put everything all together and come up with a surface fractionalization pattern, then you find something that's potentially consistent with topological insulator. But of course, the understanding of topological insulator is starting from band structures and all that. This is a strongly interacting limit of the theory. It's a very strongly interacting perspective of understanding topological insulator and making the connection from single non-interacting fermion to this fractionalization pattern is highly non-trivial. And I like especially like the derivation of Max Medlinsky, where he started. I think the MIT group also has similar derivations, where they started from single Dirac comb and break symmetry, or induce superconductivity and see how the vortex transform, and then condense vortex, and go to some anyon theory with 96 anyons, and then quotient it down to anyon theory with 24 anyons. So that's what we have. In the end, you have a highly complicated surface theory with either 12 anyons or 24 anyons, but that's the prediction. That if the fermionic topological insulator surface state can ever be gapped without breaking symmetry, that's what we should see. Okay, whether that can be really realized, I don't know, because we don't know what kind of interaction, realistic interaction, will be able to induce that kind of surface topological order. But of course, it's a possibility. On the other hand, for topological superconductor, this becomes a very useful way to think about topological superconductor, because if we originally, when we think it in the free fermion picture, we know that the topological superconductor has a Marano cone on the surface, and that the Marano cone has certain chirality, and it seems that no matter how many copies of this cone you have on the surface, it's always anomalous, at least from the free fermion picture. And I think people believe that for quite a long time, that the classification of topological superconductor in 3 dimensions is Z. But then later, Alexei said it's Z8. And of course, Alexei has a different way to derive it. He put mass field on the surface of topological superconductor and tried to disorder it. What we did is to think about surface topological order. Surface topological order is already a strongly interacting perspective. So if we can see whether the surface topological order is trivial or not, then we can determine that under strong interaction, what should be the classification of topological superconductor. And it turns out that 16 copies of the surface topological order actually becomes trivial, meaning that it can be realized in 2D without anomaly. So that's consistent with Alexei's derivation that the classification of topological superconductor should break from Z to Z16. Okay. Right. Okay. Oh, did I say that? Sorry. Z16. Sorry. It's Z16. Yes. Oh. Okay. Right. So yeah, that's a long answer to your question. Right. Okay. Sorry, I guess I already run out of my time by a lot.
Good job.